I'm covering a technique for analyzing a truss called the method of joints. Okay, so to get started, I'm going to give you an overview of sort of the big picture. Normally, when you do an analysis of some type, like this in engineering, you need to write governing equations, and then we've talked about this before. There's the equation writing, and then there's the solving. Okay, so you can separate those two things out. But this method of joints, actually, you can sort of play around with this and come up with an easier path through the process of solving the equations. Okay, so we'll talk about this as we go. But the general idea here is that you can do a free body diagram of the entire truss and look at the reaction forces from that free body diagram. We've talked about how you write equations using sum of forces in the x direction, sum of forces in the y direction, and sum of moments about any point. All that still applies. Okay, so we still have that at our disposal for analyzing a truss. But what we're going to do to look at the internal forces within the truss members, you can do a free body diagram of each joint. So we're going to talk about how that would work and some assumptions you make for that. And then, as I mentioned, you can map a path towards solving these kind of problems by looking at the joints in the correct order. All right, so the order means you have to have a starting point, and the starting point generally is look for joints with two unknown forces. If you have two unknown forces, you can write two equations, two unknowns. We know that we can get started doing that. So that's a preview of the method that we're going to do. Hopefully it'll make sense as we go through a specific example. Okay, so in this specific example, I have a truss and it's supported with a roller and a pin. There's some additional theory that goes behind analyzing trusses that talk about when can you analyze a truss, what situation is set up to where it's even possible to analyze a truss. And it turns out you have to have the truss constructed correctly and supported correctly so that you get an equal number of unknowns and equations so that you can solve those. That's beyond the scope of what we're going to be talking about with trusses, so we're going to assume that the truss is constructed in a way to where an analysis is possible. Okay, so maybe you're thinking, what examples would you give me where it's not possible? If I change this roller at point B to a pin, then this would be over-constrained and our techniques for solving this would not work. Okay, so we're going to assume that the problem is well posed and move on from there. Okay, so I'm going to skip the step of doing a free body diagram of the entire truss because it turns out in this particular case you can solve for all the forces in the truss by just using method of joints. But in general, that's a place to get valid equations. All right. So where I'm going to start is let's just talk about what it would look like to do a free body diagram of a member of a truss. Okay. So let's not even talk about this truss that I've drawn here. Let's just pull a member. All right. It operates at some angle. All right. It's connected at joints. Okay, and so I can do a free body diagram of just the member, and then I could do another free body diagram of the joints. Okay, so I'm just pulling one member out of the truss. If that member is in compression, then there'd be external forces that push it together. Okay, we talked about that in the intro to trusses video. So if I push this together, this would be in compression. Okay, now let's take this joint. Okay, this joint, I'll change the color. Let's take this joint right here, pull that out, and do a free body diagram. Okay, well, what we know is that there is reactionary forces. So if the joint is pushing on the member, then the member is pushing back against the joint. Okay, so you notice here, if I called this point A and this point B, this force moving through the member would be FAB. All right, so if I do a free body diagram of the joint, okay, FAB points into the joint. Okay, so that gives us something to remember. I'll write it in red. Okay, arrow, the force arrow, into the joint implies compression. Okay, so let's think about tension. Okay, let's draw a different joint, a different member. Okay, we have a couple of places that we can pin that. If it was in tension, we would have forces pulling this to make it be in tension. Okay, so then if I pull out the joint and do a free body diagram, okay, here's the free body diagram of the joint. Okay, if I have an external force pulling on the member, okay, then what's going to happen at the joint? Okay, well, because this is under tension, this is going to pull at the joint. Okay, so moving away from the joint. Okay, so that gives us the other condition, the force arrow moving away from the joint implies tension. Okay, so those are the things we need to know to draw free body diagrams at the joints. Okay, so I'm going to circle all this and make it smaller and move it out of the way. Okay, so at this point, what I want to do is apply some of these ideas to this truss that's shown in the figure. And before we get started, let me talk about some angles that are going to be important. Okay, so I take a look at this horizontal line and the angle of this member AC. We'll call that theta 1. Okay, and then with a different color, if I take this line, this horizontal, and this angle, that would be theta 2. Okay, so that gives me the directions of the member forces FAC and FBC, and I know that FAB is completely vertical, so that we know that angle as well. It's just easier. Okay, so I could get theta 1, change that back to purple. Theta 1 is known to me because I can do an arc tangent of rise over run. This has a rise of 0.4 and a run of 0.75. Similarly, I can get theta 2. It's an arc tangent. I'll change colors. Arctan, rise over run. Okay, so the rise is 0.4 minus 1.4, so it's a rise of 1 for a run of 0.75. So at this point, I know the angles theta 1 and theta 2. Okay, so the next step is to start looking at the joints. All right, so I can do a free body diagram of each joint. Okay, so I'm going to start over here and call this joint A. All right, and at the pin, I know that I have a reactionary force at the pin because it's a pin. All right, holding up the truss. There's an AX and an AY. All right, but then I also have forces acting on the pin from the members. All right, so looking at my diagram, I know I have FAC and FAB. All right, so I'm going to draw all of the member forces as if they were in compression. I'm not going to try to guess. Okay, I'm just going to always reference things in a certain direction. Now, I'm an electrical engineer, and it turns out when you solve circuit problems, you have to make assumptions about voltages and currents and which directions they flow. And I do the same thing when I do that kind of analysis. I always just assume one thing and then let the signs of the mathematics tell me if I'm wrong, or tell me if, it's not being wrong, it's just a matter of how do you interpret the direction of a positive force. All right, so I'm going to draw both of these forces from the members into the joint, okay? And so what does that mean? Is the joint in tension or is it in compression? Okay, well, if it's going into the joint, it's in compression. Okay, so I'm drawing this as FAB and FAC. All right, then I take a look at this and I thought, well, what do I know? I don't know any of these forces. I don't know FAC, I don't know FAB, I don't know AX, and I don't know AY. I can write two equations by resolving forces in the x direction, resolving forces in the y direction. Okay, two equations, four unknowns. Joint A is probably not the best place to start if I'm going to try to solve this problem. Okay. All right, so let's go to joint B. All right, so at joint B, I have a reactionary force from the horizontal roller. It's got to be normal to the roller. So I'm going to put down force B. Okay, then I have FAB, and again, the way I'm solving these, I'm drawing everything in compression. Okay, it's possible to do this without drawing everything in compression. It's just more error prone in my opinion. Okay, so we're going to draw FAB as coming down. It's coming down because I want the force to be into the joint. All right, meaning compression. All right, then I also have the force coming from FBC. Draw the arrow into the joint. Okay, this is the picture for joint B. I take a look at this. I have three unknowns. I don't know FAB, I don't know FBC, and I don't know B. All right, I can only write two equations. Okay, so finally, let's do joint C. Okay, at joint C, I'm going to draw all the member forces into the joint. Okay, so FBC and I can't remember the letters, AC. And then I have the load, the 2.8 kilonewtons moving down. Okay, so at joint C, I'm feeling a little optimistic now because I know 2.8, that's a known force. I don't know FBC and I don't know FAC. So that was the hint I was telling you at the beginning. This would be a good starting place if I was going to try to solve this problem. Because at joint C, I can write two equations, two unknowns, that would let me solve for FAC and FBC. Okay, so once I know that, then I know one of the forces in this, I know FAC, and I would know FBC. So from joint B, right, there's only two unknowns on joint B. This one's unknown, but I know this one, so I could then solve for FAB and B by writing two equations, two unknowns. All right, and so once I have that, that lets me move to here where I know FAB, I know FAC, two equations, two unknowns would let me solve for AY and AX. Okay, so that's the map through the problem. I start here at joint C, then I move to joint B, and then I move to joint A. And I could solve those at each stage, and I wouldn't have to write, a big matrix of equations. Okay, so let's get started with that. And, I tell you, you don't have to write this to where you write a matrix of equations, but then ultimately I'm going to give you MATLAB that has a matrix of equations, and that's going to be how we find our answers. All right, so let's get started with joint C. Okay, so looking at joint C, what I'm going to do here is something you've already know how to, you should already know how to do. I'm going to resolve these forces into their components. All right, so if I did sum of forces in the x direction equals 0, then I would have FAC is moving to the right, but I need to resolve that into the horizontal component, so I would take FAC cosine theta 1. All right, and then FBC is also moving to the right, so it would be plus FBC cosine, to resolve it in the x direction, theta 2. And there's no more forces moving in the x direction, so this would be equal to 0. All right, so still at joint C, now we do sum of forces in the y direction equals 0. I'm going to take y being up, all right, or positive is being up, okay, and I would have FBC sine of theta 2. Normally I would write these in the same order, okay, so I'm going to move that over here. Sine of theta 2. I'm going to give room for the whole thing. Okay, and then I have the 2.8 kilonewtons is moving down. Okay, and then I also have the FAC component is moving down, so this would be minus FAC sine theta 1. Okay, sum of forces in the x direction gives me one equation at joint C, and sum of forces in the y direction gives me the second equation. I could then solve for FBC and FAC. Okay. All right, so I'm not going to do that. I'm going to just move on to the next joint. Let's look at joint B. Okay, so at joint B, sum of forces in the x direction, I have B right here. FAB is completely in the y direction, so it's not involved. Okay, then I have, moving back to the left, I have FBC cosine, and this angle was theta 2, right? So theta 2 is equal to 0. That's the first equation at joint B. The second equation at joint B, sum of forces in the y direction, the B force moves completely in the x direction, so that's not present in this equation. Then I have minus FAB, because FAB works down. And then also FBC is working in the downward direction, so it's minus FBC sine theta 2 equals 0. Okay, sine theta 2 to resolve the BC component in the y direction. And so that gets me the second equation. All right, two equations, two unknowns, I can solve. Okay, why is it two unknowns? Because I already knew what FBC is. All right, and so that lets me solve for the unknowns B and FAB. All right, and finally, joint A. All right, so I look at the free body diagram and I see I can write the equations for joint A. Let me just copy this over. Put that right here so we can see it. Sum of forces in the x direction, I have AX. Okay, I have minus FAC cosine. Okay, that would be theta 1. And those are the only two forces in the x direction. For AY, I have AY in the positive direction, so it's plus. In the up direction is positive. I have plus FAB. Remember, I drew all the member forces as if they were in compression, so that goes into the joint. That's the reason that goes up. All right, and then I have plus FAC multiplied by sine theta 2, no, sine theta 1, to resolve that in the y direction. And that's it. equals 0. All right, so here's the first equation at joint A, here's the second equation at joint A. All right, so at that point, if I was solving this, I know FAC because I had solved that from joint C. I know FAB because I solved that from joint C as well. And so two equations, I don't know AX and AY, but I can use these two equations to solve them. All right, so that's an example of the method of joints. I've included some MATLAB code here that you can take a look at. Remember, there's the writing of the equations and there's the solving of the equations. Now, I want to caution you that if you do this all at once with this set of equations that you write, you have to assume the members are in compression from joint to joint to joint. Okay, you have to assume something consistent. So in other words, if you assume member AB was in compression at joint C, you need to assume the same thing at joint A, okay? Because you're solving everything at once. All right, if you iterate through this, it's possible to change the assumption on the compression and tension as you go and step through it. I just find that a little confusing. I just always like to stick with, let's draw all the members in compression. My mechanical engineering professor friends, I haven't talked to them about this. They may have a different opinion of that, but that's just my technique for solving things. Okay, so hopefully this helps. We're going to do more examples on this because it takes a while and it takes some practice to get it. Oh, before I go, let's take a look at our answers here. Okay, our answers show FAB as negative. Okay, we assumed FAB was in the member AB was in compression. What that means is that FAB is equal to 2 kilonewtons. Remember, I dropped the K in the when I wrote the equation, so all my answers are in kilonewtons. FAB is 2 kilonewtons and it's in tension. Okay, FAC is 1.7 kilonewtons and it's in tension. And then FBC, that's a positive result. Okay, so I'd drawn everything to be under compression, so this is kilonewtons compression. Okay, so you see what I mean? The signs take care of themselves at the end. I drew everything in compression, but I got some negative answers. All the ones that are negative mean that those particular members are in tension.